I've been asked by quite a number of you to take a look at the C# concept of a span. Now, spans have been around in the C# language since around about version 7, so it's not brand new, but we're going to take a look broadly at what they're there for. And the thing to bear in mind about spans is their benefit is in terms of performance. So in the right situations, you can use them to make your code run faster. And the reason they do that is they give you fine-grained control over exactly whether you're going to store your objects on the heap or on the stack. Now, we did a video a way back on the difference between heap allocation and stack allocation, the difference between reference type and value type. So do take a look at that if you're not familiar. We're going to assume that and take a look at how these spans work. So let's dive in on that. And what I'm going to do is in this console application, I'm simply going to create an array of ints. So we'll have an int array. We'll call this A1 equals, and then we can just initialize that to some numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And that has created for us an array. And remember, an array is always a reference type. So even though ints are value types, the array itself sits on the heap. But because ints are value types, the integers sit directly within the array. If this were an array of a reference type, like say a string, then the array would contain references and the references would be somewhere else in the heap. But as it is, we've got something on the heap. And then what you can do with an array, you could do something like this. We could say int array A2, and we could take a subset of array 1. Various ways we can do that. The easiest way is just use the idea of a range, which again, I did a video on a while back. So we could say 2.6. So that's going to be elements 2 through to 6 exclusive. So that 6 isn't going to be in there. But what we can see then is if we print those out, so if I just do a for each var I in A1, and then console write line of I, and then do a similar thing for A2, and then put an extra line break in between them. And if we run that and just drag over the console, we can see we've got the full collection of 0 through to 9, and then we've got the range 2 through to 5 because the 6 is excluded. But the thing about that is you can see A2 is an array of ints in its own right. And that means that it's a copy of the original A1. And we can prove that easily enough, because if I say something like A2 square bracket 0 equals 500 and run that one up, then we can see that we've changed 2 to 500 in the copy, but we haven't changed 2 to 500 in the original. So we've allocated two arrays there, two things on the heap that are using up memory, which isn't a huge problem, but will also need garbage collecting when they are finished with, and that's really where the benefits of the span start to come in. So what we can do is make a very slight change to that, and rather than extracting the range 2 to 6 from the array, we can say A1 dot as span, and this converts our array into this thing called a span. And that means that when we do that, we're no longer getting back an array of ints, we're getting back this idea of a span of ints. And that has done something completely different, because now, although A2 is looking at the same thing, so that 2, 3, 4, 5 from the original array, it's actually looking at it in the original array. And again, we can demonstrate that, because if we run this one now, we'll see that the 500 has not only been set in the span at position 2, but has been set in the original as well. And so that's telling us that they are the same array. There's only been one allocation on the heap, and then this span is simply looking at that. And that's basically what a span is. It's a window onto an existing array or some other contiguous collection. We'll talk in a moment about exactly what you can have a span of. But that's what we've got there. So we've only got the one array, and then the span is actually a value type, a struct. So the span exists on the stack. So we've allocated no heap memory for that. And all that is being stored in the span is a reference to the initial position in the original array. So position 2 in this case. And then also a length. So the fact that it's got 4 elements is calculated. So 2, 3, 4, and 5. So that's all that's being stored additionally, and that's all being stored on the stack, not the heap, so there's no further heap allocation. So that as span is something that we have on our array, and in fact you don't always need to use it, because if you take an array and simply assign it into a span, then that happens implicitly. In this case, though, rather than the span looking at a subrange, it's looking at the entire of the array. So A1 and A2 are just alternative ways of looking at the same thing. And if we run that, then we can see that element 0 of A2 is element 0 of A1, and so we've just changed that one directly. So various ways we can do that. There are various other ways we could get subranges of it. So if we did this A1.asSpan, we could then do a slice, and then we could say something like slice starting at 2. Thing to watch out for, a bit different from the range though. Remember, the range gives us the lower bound and the upper bound, whereas the slice gives us the lower bound and the length. So I would have to put 4 in there to get the same basic idea. So when we run that one, we can see we're getting the same thing, that we're starting at 2 and we've got 4 elements. So you can use the slice or the range, up to you. They really do exactly the same thing. The other thing that we can do though is actually the asSpan itself will take parameters exactly the same as slice. So actually, in that case, we could have just done 2, 4 in there, and again, that would give us the same behavior. So various ways we can get hold of these, but in all cases, although the original array was allocated on the heap, the new span has no new heap allocation and just this very small stack allocation, which is what it needs to record the position and the length of its window onto the array. Other things that we can have spans of, as I said, we can really have them for anything that is a contiguous collection of items. So an array of any data type you like, but also we can have spans for strings. So if I were to just comment that out, and then what we'll do is here, we'll say var struspan equals, and then let's just say hello world, and then do as span on there. So that will give us our struspan. And if we look at the type of that, you can see it's slightly different because this is now a read-only span of char because it's a string. But the point being that because strings are immutable, you can't change hello world. So when you've got this idea of a span onto it, you can't do what we had with the regular span of assigning into it. We can only use it for reading. But we can still do that. So if I just grab the for each loop again and then change that to struspan, then we just see that we've got each of the characters coming out individually as one item in the span. So works for strings, but it's got to be read-only. Really doesn't work for much else. If I were to do list of int il equals new list of int and just put some values in there, doesn't really matter much what, then if I were to try and say span of int a3 equals il, well, you can see we're getting an error because there's no implicit conversion, and that's actually happening because there is no explicit conversion either. So we don't have the asSpan method available on a list. And the reason for that is because there's no guarantee that the data stored in a list is going to be a contiguous chunk of memory. It could be broken up depending on the implementation. That's true really for all the other collections. With an array, with a string, in fact with a string, we don't need the asSpan now because again, here it will do the implicit conversion, so that will work perfectly well. So the only things really that we can do this conversion into a span are strings, are arrays, or another thing that's not used that widely, a thing called an array segment, which actually is kind of a precursor to a span. Spans work rather better at it. But it's still pretty powerful in terms of memory management for those things to which it applies. Now, another step further we can take with spans is this. Something that's been around in C# for quite a long time is the idea of stack allocation of an array. So what we can do, rather than having our int declared like that, which is actually really an abbreviation for equals new int 10 and then initialized to those values, just to put it in its long-winded way. But that new is what is allocating our array on the heap. But instead, for quite a while, we've been able to use this word stack alloc. And that says, don't give us the new array on the heap, give it us on the stack, which again is going to give us benefits in terms of garbage collection. There's nothing to be collected. We can see the problem there though. That is that traditionally, when we do this sort of thing, this is counted as unsafe code. The way that actually has to be declared is as an int pointer, and then we would have to wrap that code in an unsafe block, and we'd also have to activate unsafe on our project. So we allow unsafe, and then we can see that that's working. What that's done in our project, just to take a look over here, is it's done that allow unsafe in there. But unsafe code is, as the name suggests, unsafe in terms of memory management and that sort of thing, something we should avoid. And that's actually something that's been improved with the introduction of this idea of a span, because now we can do a stack alloc not into a pointer, but into a span. So if we do span of int again, because it's an array of ints, and then that is going to be perfectly happy. And once again, we can just loop through that in the same sort of way, and it will work just the same as before. But now we've done no heap allocation at all. So that is a program, you can see it's still working, that runs entirely within the stack and no heap allocation whatsoever, which is pretty useful in certain situations when you're worried about the overheads of heap allocation. And in fact, let's take a look at a slightly more practical example of where this can be useful. So we've seen it just running through on some simple collections and strings and that sort of thing, but let's try something else. Let's take a look at this struct that I've written in advance called point3d. So we can see here, I've done it as a record because that just makes it nice and easy to generate, but it's a record struct. So this is a value type. This is going to tend to live on the stack. So again, no allocation. And the only thing I've done so far is given it an override so that it's got a toString that will print out the coordinates x, y, and z. And so if we go back to our program here, if I just say var p equals new point3d, and then give it some values in there. So let's go for 1.1, 2.2, 3.3. And then the only thing we can do with it, as we've seen, is we can say console write line of p, that will call the toString, and we get the results out as we expected it. But once you've got something like that, a numerical type, what you very often want to do, just like we can do with ints and doubles and everything else, is parse it. So what I'd like to be able to do is actually say something like this. Just like we could say var I equals int dot parse, and then as a string, parse in 42, I'd like to be able to say var p equals point3d dot parse, and then pass the data in really in the same way that we saw it coming out of the toString. So in brackets, comma separated, and then the double values for each one of those. So I would like to be able to generate my 3D point that way, and then obviously when I do the toString, I'll just get that same string out again. So let's introduce that. So let's just go over to our point3d, and on here, I'm going to have a public static. It's going to return a point3d. It's going to be called parse, and it's going to take a string that we'll call input. I'll put in a bit of exception handling because obviously when you're parsing a string, things can go wrong. So I'll catch absolutely anything, and then I'll just throw a new format exception, which is what you normally get from a parse when things go wrong, and then just input in incorrect format, and then we'll take that exception E and use that as the inner exception. Now I have to say, I'm not going to be really writing code that tests for every possible wrong input, so there may be a few gaps here. That's not the point of what I'm doing. I'm focusing on the correct input, but we do need to have that in there. And then what we need to do is this. So we're trying to convert something in the format like that on the toString back into our point3d. So first thing that we do is we need to get rid of the round brackets. So I'm going to say var items equals input dot replace, and then we'll get rid of the open round brackets. So replace an open round bracket with a blank, and then I'll do another replace and get rid of the close round bracket, replace that with a blank, and then I'm going to split what's left on the basis of the comma, because that's what's separating it, and that will give us an array containing the x, y, and z values, but obviously as strings. So then we need to convert those into numbers. So the last thing we need to do, we can say return new point3d, and then we can simply say double dot parse, and then items 0, and then just the same thing for the other two, and obviously make those items 1 and items 2. And then that should be working okay. So if we run that one, we can see we've converted it from a string and then back to a string, but the string that we got out again is reading correctly 1.12.23.3. And obviously we could just put a break in the program there, and we should be able to see at that point there that P contains those correct values. So that's worked perfectly well. The thing about that is, though, it is doing a surprisingly large amount of heap allocation, because the thing you always have to bear in mind with strings is, because they're immutable, every time you do anything to them, you are creating new strings. So what we're doing here, apart from the fact we're creating strings for the open brackets and the closed brackets and that sort of thing, the first replace allocates a new string, the second replace allocates a new string, and the split, presuming there's 3 of them, is going to split that into 3 new strings. So lots of new strings being created, which isn't a huge overhead, but they all have to be garbage collected at the end. And we can demonstrate that because I've set up some benchmarking in here. So I'm using the benchmark.net library, which again we looked at a few videos back, so if you want to know the details of that, but it's pretty straightforward. And so what I've got in here is this benchmarking, and there I've got my input string, and I'll actually comment that one out for now because we're not going to have that one yet, but I'm going to benchmark the slow way, and the way we simply do that is we're going to say return and then point3d dot parse, so the thing that I've just written of that input. So I'm benchmarking that. You'll notice I've also put the memory diagnoser. That means the benchmark will give me some additional information about memory usage. And then back in the program, all I need to do is say benchmark runner, is say benchmark runner.run, and then the class that I've got the benchmarks in, which I've just called benchmarks. Get hold of the namespace for that. And then remember, you can only benchmark a release build. So we'll run that. That will take quite a long time to run the benchmarks, so we'll whiz through to the future and see the results. And then when we take a look at that, we can see there's the slow way. So it's taking around 180 nanoseconds. But the thing to notice, it's allocated 248 bytes on each one of those to do that, which may not be a huge amount, but if you're doing lots of this, processing a big file or something, they would all need to be garbage collected. That said, that's not really very interesting until we compare it with something else. So let's now use what we've been talking about in terms of stack alloc and spans to produce a much faster way of doing the parse. So what I'm going to do is take that existing parse, and I'm going to rename this one parsed fast, just so we can see the difference. And same sort of exception handling, but we're going to try and do this without any memory allocation whatsoever. Obviously, the string to come in must have been allocated, but inside this function, we're not going to do any heap allocation at all. So let's delete that, and then let's start working on that. So the first thing I need to do is take that input and turn it into a span so that I can start manipulating it in the appropriate way. So I'm going to use a read-only span of char, and don't need the split on there. I'm just going to take the whole of that input. Then I'm also going to need a span into which I'm going to put the results. So this is going to be a regular span of doubles, because that's my coordinate type. And so I'll call this coords. And I'm going to say that equals, and this one we're going to stack alloc, and I'm going to stack alloc that, and it's pretty simple. It's going to have 3 elements. But something to watch out for with stack alloc is it doesn't guarantee that elements will be initialized to their default value or anything like that. So when you do a normal array on the heap, if it's an array of doubles, each one of those guaranteed to be initialized to 0.0. But with stack alloc, although it very often happens they are initialized, according to the documentation, it's not guaranteed, and therefore we shouldn't assume it. So better thing to do is just initialize these to 0, 0, 0. That will give us an empty set of 3 coordinates. Then the next thing we need to do is we need to also have a further span of char, which we're going to use to store each of the numbers, but still in their textual form. So I'm going to call this number. And so, for example, if we've got the number 1.1, this is going to contain the 3 characters 1 and the decimal point and 1. Now, a slight problem we have here is we don't know how big the numbers could be. So how many digits they're going to have. And what we're going to do is give it a reasonable max. Because what I can do here, when I do the stack alloc, I can actually do it for the length of the entire input. So I could do chars.length, and clearly no individual number in that input, which is the same as chars, can have a length greater than the input, so we know that's going to be safe. Now there's one other caveat here about the nature of stack alloc. Stack alloc allocating on the stack, therefore there is a risk of a stack overflow if you allocate too much. And there is a form of denial of service attack where a hacker, if they passed in a really, really long string here, that could be so big it crashes the program by overflowing the stack. So ideally, we should be putting some kind of safety check to make sure that's not too big. Typically, you might do around 1,000 elements, something like that. But I'm not going to bother with it here, but it's just something to watch out for. So that's going to contain each of our numbers in turn. Another thing we're going to have to do there is, again, worry about this initialization. Now, our number characters don't want to initialize to 0, which would be the default for a char. They want to default to spaces because the double dot pars that we're eventually going to use does understand that it can ignore spaces. So the other thing we can do here is we can say number dot, and see a couple of things. We could have done clear, and that would simply set all of those chars to 0, which we don't want. But the alternative is fill, and then we can just put a space in there. So that means that our number, however many characters it's got, all of those are spaces. Notice though, absolutely no heap allocation at this stage. Now we've got to do the processing. So what we're going to do is introduce a couple of other variables. I'm going to have a count, and that's going to tell us whether we're dealing with coordinate 0, 1 or 2 for x, y or z. And then I'm also going to put another one called pos for position, which is going to tell us where in this number that contains all the digits we're dealing with on a particular number. So is it digit 0, digit 1, digit 2, that sort of thing. And now let's put in a for each loop. And that's going to be for each char in chars. So we're looping through the read-only span of chars. You'll be noticing already this is vastly more complicated than the much simpler code that we had when we weren't worried about performance, and that's often going to be the case. So you don't do this sort of thing for fun, you do it when you really have a serious performance problem to solve. But what we're then going to do is, well, firstly, we're going to say if c equals, and then open round brackets. Well, we know we want to ignore those, so we'll just do a continue in that case. At that point, we should be at the beginning of the first number, the x coordinate. So we need to start transferring that from the read-only span of chars into our number. So what we do is pretty simple. We just say number, and then we can say pos plus plus equals c. So if the number coming in were 1.1, we'd get a 1 going into number 0, then plus plus would move us on, then the decimal point would go into number 1, and then the second 1 would go into position 2, so that would have built up our number as a span of chars with lots and lots of trailing spaces probably, but that's not going to cause us a problem. Next thing though we need to do is what happens when we come to the end of the number and we want to move on to the next number from x to y and y to z. Well, we know we've come to the end of the number because either we're going to hit a comma, so if c equals comma, or if we hit the end close bracket, so that's going to mark the end of the z. So either of those circumstances mean that we're either moving on to the next number or we've finished the last number. So what we then need to do is take the contents of the number as it is and actually turn that into a number. So we need to say coords, remember that's our span of doubles, and then that's, remember, what count is there for. So we're going to say count plus plus, so it'll put it into 0 and then moves on to 1, or put it into 1 and then moves on to 2. And then we're going to do our double dot parse. And the nice thing here, and I don't think we could do this if this weren't the case, obviously normally what you do is you parse a string, but if we whiz down through the overloads, you'll see we've also got a parse for a read-only span of char. Now in our case we've got a span of char, but there's a conversion in that direction, not in the reverse direction, but you can convert from span to read-only span. So all we need to do is put in there our number, and that will give us the actual double that we want, again, without any heap allocation. Now we've just got to do a bit of tidying up to move on to the next element. So we're going to set pos back to 0, because we're starting again with a new number this time. And then we're also going to repeat our number dot fill space so that it's blank. We're not going to get any of the previous number left over. And then once again, we don't actually want to process the comma or the close round. We don't want to put them into the number. So we again do a continue at that point so that we jump round to the next part of the loop. And so that's going to keep going round. It's going to read the x coordinate, the first number, and convert that into an actual double. Then it'll move on to the y, the second one. Then it'll move on to the z. But then obviously it will have reached the end of the read-only span of chars, and so it'll finish. And then finally, all we have to do is at the end of all that, we can simply say return new point3d, and we can just put in those coords, which already contain the doubles, so we don't need to do the double dot parse at that point, but that will give us back, in a very much more long-winded way, but with absolutely no heap allocation, that should give us back our converted number. Let's just go and check that first to make sure there's no bugs in there. So let's comment that bit out, but then open up this bit. But remember, we are now going for our parse fast, and we'll just run that. And we can see that's worked okay. So once again, we're getting out what we put in, so that parse fast has worked. So no bugs. We should obviously do unit testing and that sort of thing to be really thorough about that. But now what we can do is actually do the benchmarking on that. So let's put our benchmarking back in, and then in the benchmarks, we'll uncomment that second one, and we'll change that to returning the point3d, but this time using the parse fast. And then let's run that. Again, we will speed up time so that we don't have to wait for too long. And if we take a look at that, we can see that comparing the fast way and the slow way, the fast way is faster. So we've got 157 nanoseconds versus 177, so just about 90% of the time. So it's a reasonable improvement, but that's not really the big benefit. The benefit is when we look at what's happened on the heap. So we've got the number of allocated bytes, remember, was 248 for the slow way, but absolutely 0 on the fast way of doing it. So that's the big benefit, because the thing to bear in mind, all of that memory that's been allocated has to be deallocated by the garbage collector. If you're not familiar with the garbage collector, another video you can look at that I've got a link to up there that tells us all about that. But the thing about the garbage collector, it obviously takes time to do its work, and that time is not included in the benchmark because it happens later on. The garbage collection doesn't happen as part of those function calls to parse and parse fast. It happens later on when the garbage collector kicks in. So we're not really seeing the full performance ratio of these two because we're not accounting for the garbage collection, which is only going to happen in the case of the slow way, not in the case of the fast way. So it can be quite a big improvement if you're worried about that sort of thing. On the other hand, though, as we can see from looking in the code, it is seriously more complicated code, which means it's more maintenance, more room for bugs and things like that. So you've got to, like with all performance issues, you've really got to need it. Performance, as they say, is the last thing that you worry about. That's not to say you don't worry about it, but I would typically have approached this problem in that kind of way, and then only if I notice there's a problem can you start using these features. But you can see we've got some really powerful features. We've got the read-only span, which can be used to get hold of a string and start breaking it down into chars and substrings and things without doing any need for reallocation. And then combining a span with stack alloc, we can actually allocate memory dynamically, but without doing it on the heap. All of that is being done on the stack. So that's it for looking at span. Next time, what I'm going to do is actually take a look under the hood of this and have a look at the C# features and the .NET features that allow a span to work. And then maybe you could use those in your own applications, though that would be quite an advanced thing to do. But until then, if you enjoyed that, do click like, do subscribe, and I'll see you next time.